In this video, we will discuss orthonormal sets. So, orthonormal set in a Hilbert space is actually a non-empty subset which consists of mutually orthogonal unit vectors. That means a collection, a non-empty set EI in a Hilbert space H. This is called orthonormal set if number one, all the vectors are mutually perpendicular to each other or mutually orthogonal to each other, such that number one, EI is perpendicular to EJ for all I not equal to J, and secondly, all the vectors are unit vectors, which means norm of each vector is 1. If H contains only 0 vector, then it has no orthonormal set, because a norm of 0 vector is not 1. And if H consists, let us say, a non-zero vector X, then we define E as X upon norm X. Then that single vector E, that will become an orthonormal set for in that Hilbert space. So let us say if Xi, this is non-empty set of mutually orthogonal non-zero vectors in H, then we define EI by Xi upon norm Xi for all I, and the collection EI, this is orthonormal set in that case, because all the Xi's are mutually orthogonal already, and we normalize each Xi by dividing its norm, and therefore norm of each EI, that is 1 also, so it will be orthonormal set. So we have so many examples. The first example is, let us say, in the space L to N, in the space L to N, because L to N, this is collection of all the n tuples over real or complex numbers. So the standard basis E1, E2, En, this is orthonormal set in this space. Similarly, in L2, the standard basis E1, E2, and so on, this is orthonormal set, because this L2, this is collection of all the infinite sequences over reals or complex. So this these vectors E1, where E1 is 1, 0, 0, 0, and so on, E2 is 0, 1, 0, 0, and so on. So these vectors, they will form an orthonormal set. Now we have theorem A in this section, which says if we have a finite number of vectors E1, E2, En, which form a orthonormal set in a Hilbert space, and X is any vector in H, then summation of mod, theorem A says summation of mod Xei square, this is less than equals to norm X square. So let us continue. So we have to prove summation mod interior product of xei whole square is less than equals to norm x square. Further, in the same theorem, we have to prove x minus summation xei into ei, this is perpendicular to ej for each j. These two results are very easy to prove. You can see it from book. But firstly, I tell you what these two results say. So this first inequality, this says the sum of squares of the components of a vector, because here we have a vector x. ei, this is orthonormal set. So this inner product x ei, this represents actually component of vector in the direction of ei, because actually this inner product, this gives components of a vector, components of this vector x in the direction of ei. So this result says that sum of squares of components of a vector in various perpendicular directions, because ये ei's क्या है, all these are perpendicular to each other. So in various perpendicular directions, this is always less than equals to length of square of length of the vector itself. And this inequality 1, this is called Bessel's inequality for the finite case, because here are summation, that is a finite summation. Here I varies from 1 to n. So this is Bessel's inequality for finite case. Now the second relation says x minus this summation is perpendicular to ej, which means if we subtract from a vector x its components in the several perpendicular directions, if we subtract from a vector x the components of the vector x in various perpendicular directions, then the result has no component left in any of these directions, because this is perpendicular to ej. This subtraction is perpendicular to ej. That means there is no component left in that direction ej. So after that we have a theorem. Actually this is a Bessel's inequality for finite case, but we have to prove Bessel's inequality for infinite case, which means if we have infinite orthonormal set e1, e2, e3 and so on, then also this inequality holds. But for that we have to prove firstly this theorem, theorem B, which says if ei is orthonormal set in a Hilbert space H, and if x is any vector in H, then the set S, which consists of all the vectors ei for which xei is non-zero, which means x and ei are not orthogonal to each other. So this is either empty or countable. This type of set S is either empty or countable. So let us prove this result. So for each positive integer n the positive integer, we consider this set Sn, which is collection of all the vectors ei for which inner product xei mod square is greater than norm x square divided by n. Take the collection of all the vectors ei for which this square of mod of this inner product xei is greater than norm x square by n. Now Bessel's inequality says that this summation is always less than equals to x square. So if summation is less than equals to x square, that means every term is less than equals to x square. So by Bessel's inequality, Sn contains at the most n minus 1 vectors. So by Bessel's inequality, it will contain at the most n minus 1 vectors. So let us see why. If let us say Sn contains n vectors, if Sn contains n vector, then for each vector which is contained in Sn, this norm square is greater than norm x square by n. Then what is their sum? Their sum will be greater than n times norm x square by n, and that is equal to norm x square, which violates this Bessel's inequality, which says this should be less than equals to norm x square. So it means it contains at the most n minus 1 vectors. So since S is collection of all the vectors ei for which xei is non-zero, and we are seeing here collection of all ei's for which this norm square is greater than this positive quantity. So we can see that S is union of all Sn, where n varying from 1 to infinity. So by this observation we can say S is union Sn from 1 to infinity, and each Sn contains at the most n minus 1 vectors. So each Sn is finite. Each Sn is finite. So it means S is countable, or of course empty, because if each Sn is empty, then S is empty. Then we have theorem C, which is Bessel's inequality for infinite case. So here, if ei is orthonormal set in a Hilbert space H, then we have to prove summation xei whole square is less than equals to norm x square. Again we can say कि sum of squares of all the components of a vector x in infinitely many or in arbitrary number of perpendicular directions is always less than equals to norm of the square of norm of the vector itself. So we have proved already for finite case. The summation is over. So from the previous theorem, if we define a set S, which is collection of all ei for which this inner product is non-zero, then we have S is either empty or countable. Now if S is empty, then what will happen? Then we define this summation xei whole square to be 0. And if we define this to be 0, because S is empty and there is no such vector ei for which this is non-zero, so we can define it 0. So if we define this to be 0, then the Bessel's inequality is proved, because left hand side is 0 and norm is always non-negative. And if S is finite, then we have proved already. Now we prove for arbitrary S. Now third one is, because we know either S is empty or countable, that means if S is countably infinite, so the rest case is just the case when S is countably infinite. So let us rearrange the vectors in the set S by this order: E1, E2, E3 and so on, En. Because this is countable set, so we can rearrange them in a sequence. Now by theory of absolutely convergent series, we know if sum of mod of something converges, then every series every series which is obtained by rearranging the terms, that also converges, and also they have the same sum. So we define this summation xei square, this to be the summation I varying from 1 to infinity xei square. Now from Bessel's inequality, we have, from the Bessel's inequality for finite case, we have summation I varying from 1 to n xei whole square is less than equals to norm x square, and this thing is true for each n. Now since n is arbitrary and we know that this summation 1 to infinity, this does not depend on this does not depend on this does not depend on arrangement of the vectors of S. This depends only on the vectors of S. Means if this series is convergent, that means it is absolutely convergent. So by any rearrangement, the sum will not be changed. So this sum is not dependent on the rearrangement of the vectors of S, and we know this thing is less than equals to norm x square for each n, and n is arbitrary. Therefore summation less than equals to norm x square for infinite sum also. So this proves the Bessel's inequality for infinite case. है